Welcome back to Math 104. We begin video set number 10. Picking up where we left off last time, recall the empirical rule. It states that many datasets arising in real life have an approximately normal distribution, or are said to be normally distributed, meaning that the histogram of the data, when you plot it, is approximately bell-shaped, in a very specific sense as we explored last time. Before we continue, there's an important caution we need to make. When speaking of normally distributed data, the numerical values of the data are typically allowed to be real numbers, not just integers. That means that it can be written in decimal form, and there's no inherent limit to how many decimal places there could be. For example, a person's height can be 70 inches, or 70.3 inches, or 70.32 inches, or 70.317 inches. Imagine that we initially measure someone to be 70 inches, but we're being imprecise. And then we measure a little more carefully, and it turns out to be 70.3. And then we measure even more carefully, it turns out to be 70.32. We keep going, we can take more and more precise measurements. The decimals could go on indefinitely. Height is a good example of what we call continuous data. They don't have to be integers, they don't have to be one-place decimals, they don't have to be two-place decimals. There's no inherent limit to how precisely we could measure height, and therefore these decimal places could go on indefinitely. Consider the question, what is the probability that a randomly selected person's height is more than 70 inches? Since height is continuous, we do not distinguish at least 70 inches from more than 70 inches. Through most of the course, this has been an important distinction. At least 70 inches would include being 70 inches in the event. More than 70 inches does not include exactly 70 inches in the event. When we deal with continuous data, we are not making the distinction between these two. Now wait a minute, are we allowed to do that? What about all the people who are exactly 70 inches tall? To understand what's going on here, think about the heights very close to 70 inches. 70.1 inches is more than 70. 70.01 is also more than 70. 70.001 is also more than 70. We can keep going, we can keep measuring height very, very precisely, and keep finding heights that are more than 70, but not exactly 70. So if we keep going and we measure height with infinite precision, allowing any number of decimal places to appear, it is very unlikely to find someone whose height is exactly 70.00000 with the zeros going on forever. Since we're allowing all of these different numbers to count as heights, we're really looking at a portion of the number line which has all the points strictly greater than 70, but not including 70. So we're talking about heights including all of these that are listed here, but not exactly 70 on the dot. To be exactly 70 inches tall is only one point on the number line. When we're dealing with entire ranges of numbers like this, we're not going to worry about a single point. A single point isn't going to contribute anything to the probability because it's virtually impossible to find someone who is exactly 70 inches tall, truly exactly. On the other hand, recall from earlier in the course, if you flip a coin 20 times with a 0.4 probability of heads on each flip, what is the probability of at least 10 heads? Now the event of getting exactly 10 heads is not a single point on the number line, but rather this entire interval. Because there's no such thing as getting 10.03 heads. You can get 9 heads, or 10 heads, or 11 heads. So the event at least 10 heads includes exactly 10, but the event more than 10 heads does not include exactly 10, and there's a big difference. Here we have discrete data rather than continuous data. Here the data points can be thought of as entire intervals rather than just individual points on the number line. Where does that leave us now? We want to understand how this new idea of normally distributed data is related to our old idea of the binomial model. We've noted earlier how the histograms arising from the binomial model have a roughly bell-shaped appearance. And our goal is to understand just what is that connection. Please go on to the next video.